Hello, my name is Trnka. I'm undergraduate student here at the Faculty of Electrical Engineering, and I would like to present my project, which is called System for Acoustic Detection and Localization based on two microphones. So the goal of this work is to create a simple demonstration device that will be able to detect and locate acoustic impulse events, which can be, for example, a hand clap. And after the detection, we want to calculate angle of arrival estimation, the theta in the picture, for which we need two microphones. And after the computation of angle, we want to display it using a user interface. So the acoustic detection system should consist from some microcontroller and two microphones. Because the web technology is easy to implement and multi-platform, we need some microcontroller with Wi-Fi connectivity. The microcontroller ESP32, which has Wi-Fi connectivity, Bluetooth, E2S bus support was chosen, and two microphones of MEMS technology from company Novus were selected. So here is how the system works. First, we need to set up the system, which consists of Wi-Fi connection setup or Wi-Fi access point setup. Next, we have to set up the discrete memory access controller for sampling the E2S microphones and start a separate thread for data processing. So after the thread start, there is a continuous loop which reads the samples from microphones, and for every sample, it tries to detect acoustic impulse events. If some event is detected, we start to collect 1024 samples, and after the collection of sample is done, we try to compute the time delay difference between two signals and calculate angle from it, and after that display it using some interface. So to detect acoustic impulse events, the algorithm based on recurrent mean calculation was selected. Here you can see on equation 1 the formula for it. It's basically an infinite impulse response filter, and the acoustic impulse events are typical with high energy in short time. So we just have to find the peaks in a signal. So for every sample and both channels, we calculate the separate mean estimate. And if these values are greater than experimentally set constant 500, and last event was earlier than 100 milliseconds, that's because we don't want to detect acoustic reflections. The new acoustic impulse event is detected. So after the successful detection, we have to find the delay between two signals. For that, the biased estimate of cross-correlation function was selected. The formula for it can be seen here, where the X denotes the signal from first microphone and Y from the second. After the computation, specifically during the computation, we try to locate the maxima of this function and the position of the maxima, which denotes the d-hat variable. And just by multiplying it with the sample time, we can get the time delay between two signals. And also to make a better, to improve the precision, the refinement using quadratic interpolation is used, which is basically that you take the position of maxima and neighboring samples and compute the new maximum. So to calculate angle from time delay, we have to derive a formula which can be done exactly by computing asymptote of hyperbolic function, where the hyperbolic function describes all possible positions of acoustic source for specific time tau. Or the second approach is by assuming that the wavefronts are plane waves, And just by simple trigonometry, we can get these formulas, where the left one is for continuous time difference tau, or the second one on the right side is for sample shift n. So because we are sampling with a finite sampling rate, the precision is also finite, and the error caused by sample rate, finite sampling with some finite sample rate, can be computed by this, where we take difference between angle for current sample and the neighboring sample, and for our sampling rate 44.1 kilohertz and diameter between microphones 20 centimeters. Here is the plot, where you can see that in the center, near the 90 degrees, it's pretty precise, and on the sides, near to 0 and 180 degrees, it's not so good. So here is the web interface. The chart was created using a Plotly.js library. The communication is done via the server-sent events, which works on HTTP protocol, but the communication is never closed. So the server can send new messages without need of long polling methods or something like that. The displayed angle is shifted by 90 degrees, so the interval is from minus 90 to 90 degrees, and the width of the displayed orange beam is 2 times delta, where delta is error estimate from previous slide. So the final device can be seen here. It was divided into 3 parts for easier manufacture and assembly, where the main part in the middle contains the microcontroller with a voltage regulator, and 2 arms contain each 1 microphone and some additional necessary components. The power is delivered using a USB-C connector, and voltage conversion is done using a voltage regulator. So to test that, here's the testing setup, and here are some results. The source of acoustic impulse event was a simple cupped hand clap, and the mislocations caused by acoustic reflection in a small room were omitted. So you can see that in the middle, near 0 degrees, it's pretty precise. On the sides, the precision decreases, and the angles above 60 and under minus 60 degrees are really critical, so they are not displayed here. So yeah, I just showed what's the goal of this project, how I selected the solution for that, what's the final device, web interface, and some experiments. Thank you for your attention.
Thank you, Maciej, for your very interesting presentation. And now it's time for questions. I would expect, Adam will ask.
Thank you for your nice presentation. I have a question. You are assuming that there is a plane wave of the sound, but at the beginning you showed the spherical. So what is the distance of the noise or of the clap source that is needed to be expected plane wave?
It's dependent on the sample rate and distance between the microphones, but it's around 50 centimeters. But it also works for much closer distances, but the precision decreases.
Okay, thank you.
Okay, any other questions? Yeah.
Thank you for your presentation. I have just one question. What would be the possible use of this technique of acoustics in, like, for example, in industry or?
So this device is just for demonstration, but use of acoustic localization is, for example, in detecting the gunshots in public areas, or in the army for detecting from which direction the shooter is shooting, for example, some vehicle, or, yeah.
Okay. Thank you for your presentation again.